In this lecture, we'll be introducing this next section of the course, which is all about probability basics. I want to first start by emphasizing that this is probably the least important section of this course. So why do I say this? Well, this section is really all about definitions and simple rules, which you've probably encountered before, perhaps in your grade school math studies. It might be a little more advanced, but nothing in this section should surprise you. Consequently, there are essentially no exercises in this section, because there isn't really anything to exercise. As such, my opinion is that you should try to speed through this section as quickly as possible. Watch it at 2x speed, take notes, and if you have any questions, just ask on the Q&A. But don't try to think too deeply about what you've learned, as anything you might be wondering about is probably answered later in the course. So with that being said, what are we going to talk about? First, we're going to look at some definitions of probability. There's a popular notion that probability represents a frequency of occurrence. While that is true and useful, it also doesn't apply in all cases. We'll see an example of where that interpretation doesn't make sense. We'll also look at a common incorrect definition of probability, which I came across in my teaching. I found that a few students were complaining to me that one technique from statistics, called maximum likelihood estimation, seemed unnecessary because it yields the same result as what they had incorrectly called the definition of probability. So you'll learn why that definition is wrong, and also important, you'll learn the difference between probability and statistics. Next, we'll look at Venn diagrams and how they help us reason about probabilistic quantities. In particular, they allow us to think of probabilities as areas in a visualizable space. We'll also look at how to define a model of probability, and we'll look at the properties of such models. We'll also use the Venn diagrams to prove these properties, showing how they can be a useful tool for this course. In the next few lectures, we'll look at how to relate different probabilistic quantities. In particular, we'll learn about the law of total probability, we'll learn about conditional probability, and we'll learn about Bayes' rule. These are very important relationships that we'll encounter again and again in this course. So if there's anything to pay special attention to in this section, this is it. Bayes' rule is, of course, the foundation for Bayesian machine learning, which has been a popular approach to machine learning in recent decades. The next concept we'll learn about is independence. Intuitively, when two things are independent, this means they are completely unrelated, although we will quantify this more rigorously later in the course. So knowing one of the things doesn't tell us anything about the other thing. For example, which team wins the Super Bowl this year is probably independent of whether or not OpenAI will remain a dominant force in the field of AI. A simpler example might be that if you flip a coin, this won't give you any information about whether or not it will rain tomorrow. The coin flip is independent of tomorrow's weather. So you getting heads or you getting tails won't tell you any more information about tomorrow's weather. Finally, we'll look at probability trees, which are another useful visual tool for thinking about probabilistic systems. In particular, they help us visualize sequences of probabilistic events. Although this is a very simple tool, it's also very practical, and you may draw on it in your future studies. For example, probability tree diagrams can be used to derive option pricing rules in finance, and eventually lead to the famous Black-Scholes formula. So to reiterate one more time, don't take this section too seriously. It's necessary, and you should understand everything we discuss, but there are no exercises and no computation, which is mostly what this course is about. Okay, so in this lecture, we're going to talk about what is the definition of probability. So we'll call this lecture the intuitive explanation of probability. Now, the issue with this is that trying to define probability can get pretty philosophical. So I don't want to dwell on that in this course. So we're only going to spend a short while discussing what probability means, and then we're going to move on quickly because the main focus of this course is doing computation. Okay? So that being said, I think the most intuitive interpretation of probability is that it's the frequency of occurrence as a proportion. Okay, so let's write that down. So interpretation is frequency of occurrence, and then as a proportion. Okay, so as an example of this, say we have a coin and we toss it a bunch of times. Okay, and we know intuitively that there's a 50% chance that it ends up heads or tails if it is a fair coin. Okay, so we call that a fair coin, if you didn't know. A fair coin has a 50% chance of coming up heads or tails. Okay. Now, one thing to note, if you've ever done this experiment yourself, is say you toss the coin 10 times or 20 times, you won't get exactly 50%. Right? So you might get 6 heads or 7 heads out of 10, 14 heads out of 20, etc., etc. Okay, so you won't always get half. But the idea is, as you increase this number of coin tosses, the number of heads and the number of tails will get closer and closer to 50%. Okay, so as the number of coin tosses increases, we expect the proportion of heads and tails to get closer to 50%. Okay? And so if you've taken a calculus course, you'll notice that there's some notion of a limit here. Okay, so as the number of coin tosses approaches infinity, that's when we expect this proportion to approach 50%. Okay, so I think this is the most intuitive interpretation of probability. Basically, it's saying that if we did this experiment a large number of times, the probability of an event is the proportion of times that event will happen out of a large number. Okay? So one way we can write that is the probability of some event is equal to the count of that event divided by the count of all events. Assuming that we had some sequence of events and all of those events came from the same distribution. You'll learn about that later in the course, but for now it's just for intuition. Now moving on, one important thing to recognize is that this explanation doesn't always work. Okay, so does this always apply? And the answer is no. Okay, so as an example, the Weather Channel says there's a 50% chance of rain tomorrow. Okay, so does that mean we can repeat tomorrow a bunch of times and then about half of those times it will rain? That doesn't make sense. Okay, so assuming that physics is deterministic, if we ran the same experiment a bunch of times, it doesn't matter how many times we run the experiment, it's either going to rain or not rain tomorrow. Okay, because the initial conditions leading to that rain or lack of rain are the same, meaning the conditions today. Okay, so in this case, that previous explanation does not make sense. In this scenario, I think the intuitive interpretation of probability is much more general. Okay, so in this case, so in this sense, 50% probability reflects uncertainty. Okay, it's telling us what we do know and what we don't know. And so one interesting thing is that this example applies to the future, because when we're trying to forecast the weather, that always happens in the future. So this is a future example. But we can also have past examples too, which involves probability. And you might wonder, well, how can something in the past be probabilistic if it already happened? Shouldn't that be deterministic? And the answer is no, because probability is used to reflect our knowledge of something. Or in the opposite sense, how uncertain we are. Okay, so another example. This is an example I got from ChatGPT. And so we can also look to the past. Okay, so I'll probably put up this text in the video since I don't want to write the whole thing down. But it says there is a 70% probability that the Great Chicago Fire of 1871 was started by a cow kicking over a lantern in Mrs. O'Leary's barn. Okay, so I'll just write a short form of that. 70% probability that Chicago fire in 1871 was caused by et cetera, et cetera. So the cause doesn't actually matter. It's the fact that it happened in the past. Okay? And so why can we make this probabilistic statement? So this probabilistic statement is based on historical evidence. Based on historical evidence. Okay, so it's all based on stuff that's already happened. But this probability represents our uncertainty about the event. So probability represents our uncertainty about the event, because nobody actually saw what caused the fire. Okay, so I hope that makes sense. So the event has already happened, so the actual cause is deterministic. There's only one actual cause, but this probabilistic statement simply reflects our ignorance of this cause. So another way to say uncertainty, so probability represents our uncertainty, probability represents our ignorance. So it reflects our ignorance. Okay? But I'll mention one more time that we are not going to dwell on this definition because it can get pretty philosophical, and we have much more to do in this course that involves actual math and computation as opposed to this philosophical discussion. Okay, so in this lecture, we're going to talk about what is the wrong definition of probability. Okay, so what is not the definition of probability? And so the reason I bring this up is because I've actually encountered this in my teaching a few times in the past couple years from students in my courses. And so the way this came about, well, let me give you an example. Let's start with that. So here's an example. So let's suppose we flip a coin 10 times. Okay, and we get 6 heads. Okay. And so you might say, well, the probability of heads is 6 out of 10 by definition. So we'll say is p heads equal to 6 out of 10. Or another example is this. Suppose we roll a die 20 times. And we get 1 5 times. Okay, does this mean is probably of getting a 1 is that 5 out of 20 or 1/4? And so in both of these cases, the answer is no. No. Okay, this is actually, these are estimates. These are called estimates. Okay, so this is not the definition of probability. And by the way, another side note here. One student also, and I remember these instances because people not only give me the wrong definition, but they are very passionate about it. They actually get angry and emotional in the past, I've seen. And I can tell this because of the way they phrase their comments. Okay, so another thing that's been brought up is that someone told me once that die is the wrong word. And in fact, this is incorrect, meaning the person was incorrect. Okay, so die is not the wrong word. So die refers to the singular form, and dice refers to the plural form. Again, I know this is not an English class, but you can look this up in any dictionary, and you will see that this is true. Okay, so that was just a side note, but back to the main topic at hand. What is the definition of probability? So why is this not correct? P of heads being 6 out of 10, or P of getting a 1 out of 4. And the answer is that these are estimates. So estimate, we'll use a hat, let's say. P of some event. This is equal to the count of that event over the count of all events that occurred. And you might say, well, this looks exactly the same as the formula we had on the previous lecture. And that's true, but here's the difference. In the previous lecture, that's part of the definition. It talks about what would happen theoretically if we ran the experiment a huge number of times. This refers to past data we've collected. Okay, so where this expression comes from is completely different. Okay, and so where have I seen this mistake arise? So I've seen this mistake arise in the context of statistics, because this is actually the answer if you perform a process called maximum likelihood estimation, which we will probably not learn about in this course. You will arrive at this answer. So this arises from a process called maximum likelihood estimation. And this is also known as MLE. Okay, but note that the answer you get from MLE is not the definition of probability. So, not the definition of probability. And as another side note, I will probably just say prob for short throughout this course. So when you see prob, it's an abbreviation for probability. Okay, so another perspective to understand why this is wrong. So MLE comes from statistics. And so another common mistake I've seen, I guess this whole lecture is all about all of these common mistakes that I've encountered over the years. Statistics is not the same as probability. Okay, so statistics is not the same as probability. Okay, and so what's the difference? So here's the way I like to think about it. So probability is reasoning about uncertainty. Reasoning about uncertainty. Okay, whereas stats or statistics, so stats will be the short form for statistics. This is all about applying probability to data. So applying probability to data. Okay, so I think data is the key differentiator here. You'll notice that in this course, we're doing computations with probabilistic quantities, but we never use data in this course. So data is something that arises in statistics. You collect data and you analyze that data using probability, using the tools that you learned in probability. So probability is the tools, and statistics is applying those tools to real-world data. And so you'll notice, again, that in this course, we do not use data at all. So no data in this course, because this course is not a statistics course. And also, I would like to clarify what I mean by data. So data doesn't necessarily have to mean real-world data. So data doesn't have to refer to real-world data or experimental data. Okay, you can think of data as just variables, right? So x1, x2, all the way up to xn. This can be your data. And then you can do mathematical computations on this quote unquote data and come up with some interesting insights. So I'm not saying you have to actually, to do statistics, you actually have to go out and collect data or find some data set to work with. That's not what I'm saying. What I'm saying is that even just analyzing what you would do, treating your data as variables and seeing what you can do with it, that is also statistics. Okay, so in this lecture, I want to do an example to illustrate what I was talking about in the previous lecture. Okay, so example for definition of probability. And this is mostly focused on explaining why that definition of probability that people sometimes tell me is incorrect. Okay, so for this example, we're going to use a classic example in probability. Suppose we have an urn or something. Okay, there's an urn and there are different colored balls in the urn. So see what colors I can find on here. I don't know how to make different colors. We'll do it like this, whatever they gave us. So here's a blue ball, here's a green ball, and here's a, okay, that's a highlighter, but it's a yellow ball. Okay. So with this situation, so say the task is to pull a ball out of the urn and find out what color it is. Okay. Okay, and so we'll assume that all the balls have the same weight, the same size. And so without looking, you can't tell the difference between the three balls. So in this situation, we would say that the probability of getting blue is equal to the probability of getting green is equal to the probability of getting yellow, and that's 1/3. And the reason why this is that's just our belief. It arises from the physics of the situation. So I because we can say arises from physics. Ultimately, well, everything is physics. You can say the same thing about a deck of cards or a die roll. Okay, because we cannot tell the difference between the balls, we have an equal chance of picking any ball. Okay, this is opposed to doing an experiment. So doing an experiment pulling a ball out, say 100 times, and then calculating P of color would be the count of how many times you got that color divided by 100, or we could just say n if we did n times pulling out the ball. Okay, so hopefully you see the difference between these two situations. So the correct definition quantifies uncertainty, arises from physics, or just your understanding of the system, and the incorrect definition computed from data. And again, typically the computation that's being done is the maximum likelihood estimate, which you won't learn about now, but you'll learn about in stats. Okay, so in this lecture, we're going to talk about probability models, or another way of saying this is we want to build a model of probability. And so this is going to make everything we're discussing more rigorous and concrete. Okay, so let's title this probability models. And we're going to define some terms. Okay, so the first term we're going to define is sample space. Okay, and this is the set of all outcomes when one does an experiment. Okay, and we're going to use the symbol omega to represent sample space. And an example of a sample space is sunny, rainy, cloudy. Okay, so this is a set with 3 elements. Okay, and so for every problem we deal with, note that we get to decide what the sample space is. Okay, so we define the limits of the problem. So an example of how you might use this is if you're trying to model the weather and you want to be able to forecast, for example, whether it's going to be sunny, rainy, or cloudy tomorrow. Okay, so that's an example of how you might use this. Okay, so now we have the term event. Okay, so now we're going to more rigorously define this word, which we already used in the previous lecture. Okay, so an event, so all subsets of omega, the sample space, are events. Okay, so any subset. And by the way, for this course, typically in some probability courses, what they'll do is they'll have a whole chapter on set theory in order to review how that works. I'll consider that a prerequisite to this course because you typically learn that in high school. And we're not going to use it much anyway, other than the basics. So I'll leave it to you to review if needed, but otherwise I think as we go through the course, anything we do with set theory, it should be easy enough to follow along. And if not, just use the Q&A and we'll help you find resources to refresh your knowledge. Okay, so subsets of omega, so some examples of that, e.g., so rain by itself, that could be a subset. But you can have more than one element, so sunny, rainy, that could be a subset, so you can take two elements, and you can even have the whole thing, so sunny, rainy, cloudy. Okay? And so it doesn't say it has to be a proper subset, which would mean that it cannot include the whole sample space. It just has to be a subset, which means you can include the whole sample space. Okay. So the next thing we're going to define is a probability measure. Okay, that's what we're going to use the letter P for in this course. So we'll say a probability model requires what we'll call a probability measure, and we'll call it P. So called P, big P, capital P. And what it does, so which assigns for each event A, and remember we defined what an event is previously, probability P of A. Okay, so one way you can think about this is it's like a function that maps each of these subsets or events to a probability value, a number. Okay, so I'll just write that down in short form. So intuition maps subset, which we're calling an event, to a number. Okay. Now, there are some restrictions on what this number can be. So we'll say P of A has the following properties. Okay, so P of A is a non-negative number, real number, in the range 0 to 1, and the square brackets means inclusive. Okay, so if you recall that from your earlier math studies, this means inclusive, and this means exclusive. Okay, so for example, the range 0 to 1 does not include 0 and 1. And you can even do this half open interval. So 0 to 1 like that. This includes 0, but not 1. In any case, since it's square brackets on both sides, a probability value can be equal to 0 or 1, or it can be between 0 and 1. That's the point. Okay. So another property, P of the empty set. So this 0 with a slash on top, that means empty set, is equal to 0. Okay, so empty set equals the set of nothing. Okay. And so what does this represent? This is the probability that nothing happens. Okay. So as an example, just to make this less concrete, imagine you're rolling a die and all the possibilities, so the sample space is 1, 2, 3, 4, 5, 6. So this is the probability that when you roll a die, you do not get 1, 2, 3, 4, 5, or 6, which is impossible, which is why the probability of that happening is 0. And on the other hand, we have P of omega equals 1. Okay, and so this is the probability that something happens. Okay, and so if we do an experiment, of course, something must happen. So again, we'll use our die rolling example. If you roll a die and you ask, well, what is the probability that we get 1, 2, 3, 4, 5, or 6, which is the sample space? Of course, the probability of that is 1, because we must get 1, 2, 3, 4, 5, or 6. Okay, so here's another property that is a little bit more complicated. So we'll say if A1, A2, and so on and so forth are disjoint events, meaning these are sets that don't have anything in common. So no elements in common. So we'll say no overlap between those sets. Then P of A1 union A2 union, and it doesn't matter how many we have, it could be infinite, is equal to P of A1 plus P of A2, and so on and so forth. Okay, this just means that if you have disjoint events and you want to know the probability of any of those happening, it's just the sum of the individual probabilities for each of those events. Okay, so we'll just clarify here. Disjoint, I wrote that poorly. Disjoint means no outcomes in common. Okay, and so we'll end this lecture by defining what a probability model is. Okay, so a probability model consists of a non-empty set called a sample space we'll call omega. Also includes a collection of events that are subsets of omega and a probability measure P, which assigns, so assigning probability between 0 and 1 to each event with P of empty set equals 0 and P of sample space equals 1, and where P is additive as above. So using the disjoint property where all the events are disjoint, so the final property we discussed above. Okay, so in this lecture, we're going to look at how we can use Venn diagrams to help us reason about probabilities visually. Okay, so it's Venn diagrams. I'm sure you have seen these somewhere before in the sum course you've taken in grade school. As I recall, they even use this kind of stuff in like business classes and such. So I'm sure you've seen it somewhere, and if not, it's pretty intuitive. So you'll be able to follow along regardless. Okay, so, and again, like everything else in this section, we'd like to go through it quickly so that we can get to the eventual computation stuff that we're going to do later in this course. Okay, so we'll begin by, well, let's look at how we might visualize a sample space and an event. Okay, so typically we draw a big box, a big rectangle, and this is our sample space, so omega, and we denote an event as some subset of that space. Okay? And note that because this is an area, technically these are continuous sets and subsets, but this applies to discrete sets and subsets as well. Okay? So the first thing we're going to define is the complement. So if you've ever encountered this before, it's basically what you can think of as the opposite. Or in terms of this event, it's everything that is not that event. Okay, so the complement, to define it more rigorously, is a complement. We also might call it a bar, which we might refer to as not A. So not A, which is equal to the set. So it's the set of all elements S such that, so we use the colon to mean such that. So such that. We also sometimes use the vertical bar as well. Such that S, the element, is not in A. Okay, so A is a set as well, as you recall. Okay, so just to make this even more complete, we sometimes use a vertical bar instead. So not an element of A. Okay, so that's the complement. So in this diagram, everything outside of A, this would be A complement. Okay, and so you can already see how we can use these Venn diagrams to explain mathematical concepts regarding these sets. Okay. So now let's talk about the intersection, which I'm sure you've seen before. So intersection. So this is everything. So say you have two sets or more. This is everything that all those sets have in common. Okay? So we have our sample space, and we have two events, A and B. And so the intersection, I think it's pretty intuitive. It's where they intersect. And this is our omega. Okay, so we write this as A intersect B. You can also think of it as A and B. And it's the set of all the elements such that S is in A and S is in B. Okay, and you can extend that to multiple events as well. Okay, then we have the union. Union is everything in either A or B. Okay, so we draw it like this. Here's A, here's B, here's the sample space. So it can be in either A or B, which means either A or B. And we write that like so. Looks like a U, but it's not a U. And we write this as all elements S such that S is in A or S is in B. Okay, so this is like and and this is like or. Okay. So now let's do an exercise. Using set notation, I want you to show how to find the set of elements that are in A but not B. Okay, so how to find set of elements in A but not B. Okay, so we can draw this as well. So we can use our visual tool of Venn diagrams to help us. So what do we mean by in A but not B? So here's A, the event. Here's B, the event. So you want in A, but not this part. Not this part, because that's part of B. So in A, but not B. Okay, and so the answer is, well, if we take, say, the complement of B, that's this, right? So this is the complement of B. B complement. And so B complement intersected with A, that would give us all this stuff. Because this is part of B complement, and it's part of A. Okay, so the answer is A intersect B complement. Okay, so one thing we can start to do is we can start to do sort of arithmetic. So suppose we wanted to, so EX can stand for example or exercise, but you can think of this as an exercise, even though I'm thinking of it more as an example. Okay, so we can think of these three areas sort of separately. Right, so here's A, B, and here's the intersection. So we can quantify each of these three parts. So in A but not in B but not in A, and then A intersected with B. Okay, so we could write the union of A and B is equal to the union of these three parts. So in A but not in B, we wrote that as A intersect B complement, union, the middle part, which is the intersection of the two, so A intersect B, union, and then in B but not in A. So that would be A complement intersect B. Okay? So that's another example of how we can use set notation. Okay, so finally, another important set of identities to Morgan's laws, which you will see all over the place in combinatorics, set theory, etc., and programming. Okay, so really anything related to computation, you're going to see De Morgan's laws. Okay, and so the way it works in this context is, suppose we have, and again, we can draw a picture, but let's do the expressions first. So A union B, if we took the complement of that, this is equal to A complement intersected with B complement. Okay, and let's see how that works. So we have A and B. So the union of them is this whole area. Okay, and you'll notice that this is equal to, so A complement is all of this. B complement is all of this. And when we intersect those together, it's all this outside stuff, which is the complement. So all this outside stuff here, which is the complement of A union B. And similarly, we can switch where the union and intersection are. Okay, so we can have A intersect B complement. This is equal to A complement union B complement. Okay, so we might even, last one kind of got messy, so if we separate the diagrams. So A intersect B, that's this part. And we want that to be equal to, so here's A, B. The complement of A is all this. And the complement of B is all this. Okay, and so where's the only area we haven't touched? It's in here. So the complement of this, which is everything outside of that, is equal to the complement of A unioned with the complement of B. Okay, and so one other interesting thing to notice is that this is related to Boolean algebra in programming. So a relation to Boolean algebra programming. Okay, and if you've coded in Python before, you probably have used this somewhere. Okay, so this is the same as we have two Boolean conditions, A and B. So it's the same as saying not A or B. This is equal to not A and not B. Similarly, if we have not the whole thing of A and B, this is equal to not A or not B. Okay, so in this lecture, we're going to look at properties of probability models. So we're going to use the Venn diagrams that we talked about in the previous lecture to prove some identities. Okay, so properties of probability models. Okay, so here's an important one. The probability of the event A complement, so everything not in the set A, is 1 minus the probability of the set A. Okay, and so how this comes about is, so here's the sample space, and here's the event A. So you think of the area of this as 1, right? Because as we established, P of sample space is 1. And so the total probability of A plus A complement must be 1. Okay, because A unioned with A complement is the sample space. Okay. Okay, so the next one, we're going to say let A and B be two events. Okay, and we'll say A is a subset of B. Okay. If this is the case, this implies that P of A is less than or equal to P of B. Okay, and how does that arise? So imagine there are several ways to draw this picture, by the way, for the different cases. But the simplest case is just A is a proper subset of B. So B has more elements than A. So of course, the probability or the area of this region is less than the area of this region. Okay, so that makes sense. This also allows for A and B to be the same set right? So that would be when, so allows A to be equal to B, which of course would imply P of A is equal to P of B. But you can also have this situation again from above, where A is a proper subset of B. And it's simply that the probability of everything out here is 0, so that P of A is equal to P of B. Okay, so through all these scenarios, this fact above remains true. Okay, so related example. Okay, so for this example, we again have A is a proper subset of B, but this time we have inequality. So P of B is equal to P of A plus, so it implies P of B intersected with A complement. Okay, and so how does this arise? So here's our sample space. Here's A, here's B. Okay, so P of B, which is this whole area in the circle, is P of A, of course, plus P of B intersected with A complement. So A complement is all this stuff, and P of B, or B intersected with A complement, would be this ring around A. Okay, so basically adding these two areas together, which of course gives you B itself. Okay. And so the final one, which is, I think, pretty well known, is P of A union B. This is equal to P of A plus P of B, but you also have to subtract the intersection, P of A intersect B. Okay, and a corollary of this, by the way, is that P of A union B is less than or equal to P of A plus P of B. Okay, so what this is saying is the probability of the union of these two sets is less than or equal to the sum of the individual probabilities of those two sets. Okay, and so why is this the case? So here's our sample space, and let's assume that A and B intersect at some point. So here's A and here's B. So the problem, if you just add P of A and P of B together, is so you would get the probability of this plus the probability of this, or equivalently, you can think of it as the area. You would double count this intersection, which is why you have to subtract the intersection at the end. Okay, so hopefully that's pretty intuitive. Okay, so in this lecture, we're going to do a simple example of how we can use the rules we learned about to compute things. Okay, so we're not going to do too many of these examples in this section because the purpose of this section is just to identify main concepts and move on quickly to computations. So this example is going to be very quick. Okay, so for this example, we'll have a die. So the sample space is 1, 2, 3, 4, 5, 6. Okay, so those are the possible outcomes. And we want to compute. So we're going to practice using this rule. So it's P of A union B. This is equal to P of A plus P of B minus P of A intersect B. Okay. So for this example, A is going to be all the even numbers, and B is going to be all the numbers greater than 3. Okay, so this half of the set. Okay, so one way we can calculate this is to use the above rule. Okay, so we'll say P of even union greater than 3. This is equal to P of even plus P of greater than 3, and then minus P of even intersect greater than 3. Okay, so what are these? So P of even, so half the numbers are even, right? 2, 4, 6. So that's 1/2 plus P of greater than 3. 4, 5, 6 are greater than 3, and there are 6 in total. So again, it's 1/2. And so again, this is assuming this is a fair die. Right, so all the outcomes have equal probability. And notice how, again, this is based on your belief about the physics of the system. It's not based on data you collected. Just for those folks who have maybe skipped ahead in statistics and are confusing the two. Okay, and so where do these intersect? So how many numbers are even and, remember you can interpret this as an and. So who's even and greater than 3? That's 4 and 6. So that's 2 out of 6, which is 1/3. Okay, and so notice that this subtraction is necessary because if we just added 1/2 plus 1/2, we would get 1, which means the probability is 100%, which wouldn't make sense. So we have to subtract something. So this is 1 minus 1/3, which is 2/3. Okay, and so now let's look at the other way to compute this to show that they're equal. So P of even union greater than 3. So let's do it directly. So this is the cardinality of these two sets union together. So the even numbers, that is 2, 4, 6, union greater than 3, 4, 5, 6. And this is divided by 6 because that's the total number of outcomes, or the size of the sample space. So this is that. Okay, and so this would be equal to, so what is the union of these two sets? So we combine these together and eliminate all duplicates. So it's 2, 4, 5, 6, which is, the cardinality of that is 4. So it's 4 over 6, which is 2/3. So we get the same answer, and we confirm that this rule works. Okay, so in this lecture, we're going to talk about another important identity or concept. It's called the law of total probability. So law of total probability. And technically, this could have been introduced with the rest of the properties of probability models, but this one is a little more important, so I've decided to make a separate lecture for it. Okay, and so the way that it works is this. So it says that if we have a partition of the sample space, so suppose A1, A2, and so on. So these are events that form a partition of the sample space. So what does partition mean? That just means you've broken it up into pieces. So as an example, so A1, A2, A3, that would be a partition of the sample space. Another example might be like this. So A1, A2, A3, A4. That's another partition of the sample space. Okay. Okay, so because this is a partition, this means that A1, A2, and so forth are disjoint So there's no overlap between any of the A's. And notice that A1 union A2 union, so forth, this is equal to the sample space itself. Okay, and so given this, suppose we have another event, B, I guess we shouldn't have put the arrow there. Doesn't matter. Event B, what the law of total probability says is that P of B, probability of the event B, is equal to P of A1 intersected with B plus P of A2 intersected with B, and so on and so forth. Okay? And so how can we use the tools that we've learned about so far to prove that this is true? So one way to do this is to just draw it as a Venn diagram. So imagine that this is your event B. Okay, and you say you have this partition of A. So here's A1, and here's A2, and here's A3. So that's our partition of the sample space. So it's a partition of the sample space. And now, if you consider what is A1 intersects B, well, that's this. So we have the probability of that plus A2 intersects B. That's the probability of this. And then A3 intersects B. That's the probability of this. And when we add those back together, or we consider the union of those, we just get B itself, which means if we summed up the probabilities, we would get the probability of B itself. Okay, so notice that A1 intersect B union A2 intersect B, and so on and so forth. This is equal to B. And because these sets are disjoint, we can use the sum rule that we talked about previously. Okay, so let's do an example with this to see how it can work. So, example. So we have a playing card deck. Okay, so that's 52 cards. Okay, and there's 2, 3, 4, 5, up to 10, and then Jack, Queen, King, Ace. Okay, so there's 13 possible ranks, and then there's 4 suits. So there's the ranks, and there's the suits, which are hearts, spades, diamond, and clover. Okay, so for this example, we'll consider the AIs. So we'll say A1 is equal to ace, or the set containing ace. A2 is 2, and so on and so forth. All right, so A10 would be 10. A11 would be Jack. A12 would be Queen, and A13 would be King. Okay, and we'll say B is hearts. Okay, so let's say we chose a card at random. What's P of B? Well, a quarter of them are hearts, so that would be 1/4. So that's the answer that we're looking for, but we're going to use the law of total probability to see that we get the same answer when we do it using the calculation. Okay, so what is P of AI for any of these intersected with B? So for example, what is the probability that we get 2 of hearts, or 3 of hearts, or 10 of hearts? That's just 1/52. because we only have one of those cards in the whole deck. Okay, so now using this law of total probability, we could say P of B, this is equal to the sum over all I, P of AI, intersected with B. Okay, and this is just 1 over 52 plus 1 over 52, and so on and so forth, 1 over 52. And how many of these do we have? Well, I goes from 1 to 13, so we have 13 of these. So it's 13 over 52, which is 1/4. Okay, so in this lecture, we're going to discuss the concept of conditional probability. So that's conditional probability. Okay, so this is a very important concept. You're going to see it all throughout probability and machine learning and statistics. And it has to do with when you have partial information. Okay, so that's one way to think about it. So used to incorporate partial information. So you know some things, but you don't know everything. And so remember that probability is quantifying uncertainty. So you want to quantify your uncertainty given that you have some information already. And this changes from when you don't have any information at all. Okay, so let's do an example of how having some information might change the probability of some event or change your uncertainty about some outcome. Okay, so the example I'll use to begin is COVID. So we'll call COVID an event. So COVID can be either true or false. Either patient has COVID or does not have COVID. Okay, so example, so P of COVID, this is just some number. Okay, so some small number. Okay, so think of this as a patient walks into the hospital. You don't know anything about them, nothing at all. And you want to know what is the probability that they have COVID. So what is the probability that some random person who walks into the hospital has COVID? Or you could even think of it as some random person on the street has COVID. Obviously, this is a very small number nowadays because most people are not walking around with COVID. Okay? So now let's assume we have some information about this person or this patient. So now assume the person has fever and cough. Okay? And so the way we write this, so P of COVID given the patient has fever and cough is some larger number. Okay, so that's what this means. So it's P of something given something. So this means given. Okay, so obviously, if a person has a fever and a cough, the chance that they have COVID is much higher than just a random person where we know nothing. Okay, so that's one example of how knowing some information changes our uncertainty. So let's do another example, but with more concrete numbers. Okay, so example with real numbers. Okay, so consider a die like this. We roll the die. Okay, so the possible outcomes. So the sample space is 1, 2, 3, 4, 5, 6. Okay. And now let's consider just a simple question. What is the probability that I get a 1 when I roll this die? Okay, assuming that it's a fair die and not a loaded die, that should be 1/6. Okay, but now let's consider another question. Suppose I roll the die. Suppose I roll the die, but I don't show you the result. Okay, so I don't show you the result. I tell you some information though. I tell you the result is even. What is the probability that the outcome was a 1 given that the outcome was even? Okay? And clearly, the answer is 0. Because if the outcome is even, then it cannot be 1, since 1 is not an even number. Okay, but that's how we would write this. So now let's suppose I tell you the result is odd. Suppose I tell you result is odd. Okay, then we have P of 1 given odd. And what is this equal to? Well, if the result is odd, then we know it must be either 1, 3, or 5. Okay? So the probability that it's a 1, given that we can only choose from this set of numbers, is 1/3. Okay, and so that gives us a hint also for how we can calculate these probabilities. So for conditional probabilities, we can think of it as a relative frequency. So the count of the number of times we see this event divided by the total number of possibilities in the sample space. But in this case, it's now the count of the event divided by only the subset of the sample space that is given by the provided information. It would be that the number was odd. Okay, so now from this, we can talk about what is the rule for calculating conditional probabilities. So we'll call this the conditional probability rule. Okay, so P of A given B, so A and B are events. This is equal to the ratio of P of A intersected with B. And remember, you can think of this as P of A and B divided by P of B. Okay, and this is requiring, so it requires that P of B is greater than 0. Okay, and of course, this must be the case, because if P of B is equal to 0, then this event is impossible. And if we're given that, then how could there be a probability associated with it? Okay. So let's think about why this works. So the intuition for why this works. So we can think of it in terms of frequencies. Right? So P of A intersected with B, this is, you can think of it as n approaches infinity, it's the count of how many times we saw A and B together divided by the total number of, say, die rolls or coin tosses. Okay? And P of B similarly would be the count of the times we saw B divided by n. Okay, and so what is P of A given B? So P of A given B, that's just this divided by this. And that would give us, so on the top we'd have count of A intersect B divided by n. And on the bottom we'd have count of b divided by n. But the n's cancel out because it appears on both the top and bottom. So it's really just the relative counts. Okay, and this is the same as our example above, where I told you that the result is odd. So now we have only a subset to choose from. Okay, so 1, 3, 5. The count of that is 3. So we're only counting from the events that are possible given the information that we've been given. Okay. So another thing we can do is we can rearrange the above identity. So rearrange. And this is also a common form to know about. You're going to see this everywhere in probability, statistics, machine learning, and beyond. It's P of A and B, or P of A intersect B. This is equal to P of A given B times P of B. Okay, so basically all we've done is we moved P of B, which used to be here, we moved it up there. Okay, so we're going to use this a lot. And so given this, we can also talk about the law of total probability in conditional form. So law of total probability in conditional okay. And so previously we said that if A1, A2, and so on and so forth are disjoint and form a partition of the sample space. I didn't really need to say they're disjoint, because if they form a partition, that automatically implies they're disjoint. Then P of B, some other event, is equal to the sum of all the intersected probabilities. So sum over I, P of AI intersect B. Okay, but now we can use the identity above to express this in terms of the conditional probability instead. So it's the sum over all the i's, P of B given AI times P of AI. Okay, and so we're going to see this a lot later in the course and throughout machine learning and so forth. Okay, so in this lecture, we're going to go through an important identity based on conditional probability called the Bayes rule. Okay, so that's Bayes rule. And this is attributed to Thomas Bayes. Okay, so it's named after this guy. And so, although the form of Bayes rule you'll learn about in this lecture is very simple, you'll see it applied again and again throughout your machine learning and statistics studies. So this leads to a branch of statistics and machine learning called Bayesian statistics and Bayesian machine learning. Okay, so leads to Bayesian statistics and Bayesian machine learning, which I found many of my students have been interested in the past and are quite useful in practice. But for the purpose of this lecture, it works pretty simply. Okay, so basically what Bayes' rule says is how we can find P of B given A, so B and A are events, given P of A given B. So we reverse the probability, or we reverse the order of what we're given and what is unknown. Okay, and so Bayes' rule is stated like this. So P of B given A, this is equal to P of A given B times P of B, all divided by P of A. Okay, so this is Bayes' rule. And notice how it also makes use of these probabilities, which we call marginal probabilities. You'll learn about that later. But you'll remember that we can use the law of total probability to calculate these. Okay? And so let's just derive this really quick. So where does this come from? I think it's pretty intuitive. Pretty simple. So we know from our conditional probability identity from earlier, P of B given A, this is equal to P of B intersected with A. So these are all sets still, divided by P of A. Okay, so that's by definition. But we also know that P of A given B, also know this is equal to P of A intersect with B divided by P of B. Okay? We also know that A intersected with B, this is the same thing as B intersected with A, because it's just the intersection of two sets. So all we're doing really is we're moving this thing up here, and we'll change this to A intersect B. Okay, so now we have P of B given A. This is equal to P of A intersect B divided by P of A. But we also know from here that P of A intersect B, we're running out of space. I'll write it below. Okay, so P of A intersect B, this is equal to P of A given B times P of B. Okay, so we plug this in. So P of A given B, P of B divided by P of A, which is the identity we have above. Okay, so that's Bayes' rule. That's how you derive it. And we're going to see it again and again in different contexts throughout this course and in future courses as well. Okay, so let's do a simple example. So previously, so this is our example. So previously, we looked at an example that looks something like this. So we wanted to know, what is the probability of getting a 1 from a die roll? So this is a die roll again, given that the result was odd. Okay, and we know that's 1/3. Right, because odd is the set 1, 3, 5. So what is the probability that you have a 1 given that the result is 1, 3, or 5? Assuming everything is uniform, that's 1/3. Okay, so for this question, we're going to look at how to compute P of odd given 1. Okay, and so intuitively, so we can do this directly, which allows us to check the answer. Right, so we know that if we get a 1, the result is odd. And so we know this. Therefore, there is no uncertainty about whether the result is odd. So this should be probability 1. 100%. Because we know if we got a 1, we know with 100% certainty that the result was odd. Okay, but the question is, can we calculate this using Bayes' rule? Okay, so let's think about what quantities we need. So P of odd, given that we got a 1, this is equal to P of 1, given that we got something odd, times P of odd, divided by P of getting a 1. Okay, so we know all these quantities. So this, we know is 1/3 from above. Okay, this, we know that this is 1/2, because either you get 2, 4, or 6, so that's one set, or you get 1, 3, 5, that's the other set. And they both have the same number of elements, so it's 1/2. And P of getting a 1, that's 1/6, because it's a fair die. Okay, and so when you calculate these numbers, well, you get 1/3 times 1/2 over 1/6, which is 1/6 over 1/6, which is 1, which is correct. Okay, now let's do a more interesting example. Okay, so in this lecture, we're going to look at another example of Bayes' rule, but I think this is both more practical and more compelling. Okay, so this is Bayes' rule example. Okay, and so the way it works is this. So the scenario is medical testing for rare disease. Okay, so let's say this disease affects 1 in 1,000 people. Okay, so that's 0.1%. Okay, which is probably actually an overestimate for many of the diseases we know of. Right, so many of the interesting and common diseases out there are actually more rare than this. Right, if you randomly run into 1,000 people, probably less than 1 would have any particular disease. Right, think of like a high school that typically has more than 1,000 people in it. Okay, so from this, we can say P of disease is equal to 0.001. Okay, and now let's suppose we have a test that detects the disease with 99% accuracy. Okay, so this in particular requires some further explanation. So what do we mean by accuracy? And can we actually use that in this scenario? So we can, but we're going to actually better define it. So the problem with accuracy is there are sort of two kinds of accuracy, right? So the person could have the disease, in which case you could predict this person does have the disease. We call that a true positive, or we might predict the person does not have the disease, which we call a false negative. Okay, so let's write this down. So here's the prediction, and here's the truth. So they can have the disease or no disease, and you might predict disease, or you might predict no disease. Okay, so if you have the disease, true, and you predict you have the disease, true, then this would be called a true positive. Okay, if you predict no disease, that would be a false negative. Okay, if you don't have the disease and you predict that you do have the disease, that's a false positive. And if it's no disease, truth, and you predict no disease, That's a true negative. Okay, so for this example, to be more clear, what we mean by accuracy isn't really total accuracy. It's this portion right here. Okay, so what we really mean is P of positive test. So we'll call that plus, given that you have the disease. So that would be disease. This is 99% or 0.99. Okay, so conversely, the probability that you say no disease or the test says no disease, given that you have the disease, is 1%. Okay, so now the question that we have is this. Suppose a person takes the test and gets a positive result. What is the probability they actually have the disease? Okay, and of course this is using Bayes' rule, because what it's asking us to find is P of disease given a positive test. Okay, so at this point I think it's important to draw out the sample space, and you'll see why in a minute. So this is our sample space, and it's very similar to the matrix we had above, right? So there are really 4 different scenarios, right? So you have disease and positive test, you have disease and negative test, you have no disease and positive test, and you have no disease and negative test. And so why do we need this? Because this is going to help us compute some of the quantities from Bayes' rule that we need. Okay, so let's use Bayes' rule and figure out what quantities we actually need. So we want P of disease given a positive test. This is equal to P of positive test given disease, probability of disease, and probability of positive test. Okay, so the things on the top we know. So this is 99% as we discussed. This is 0.1% as we discussed. So it's just this thing we don't know. P of positive test. So the trick here is that we have to use that law of total probability. Okay, so total probability so P plus, this is equal to P plus given disease, P disease, plus P plus given no disease, P of no disease. Okay, and so why is that? Well, we can convert it into the other form with the intersections, right? So P of plus and you have the disease plus P plus and you have no disease. Okay, and so going back to our Venn diagram above, so it's plus and disease or no disease. So we're really considering this portion of the Venn diagram. And it might not even look like a Venn diagram at first because I didn't draw circles like I did before, but it actually is still a Venn diagram. Okay, so this is like that event B that we talked about earlier. And this So these are like the partitions of the sample space, right? So this would be like the A1, and this would be the A2. Okay, so now you're getting to see all that stuff from before put into practice now. Right, so we're really saying P of B is equal to P of B and, or intersect A1 plus P of B intersect A2. Okay? But it turns out, in fact, that this form, the first form we had, is the most useful. So in conditional probability form, because most of the quantities we have are in terms of conditional probabilities. Okay. So let's write these down. So P of positive test given disease, we know this from above, right? That's just 0.99. Okay, P of disease, that's 0.01. Now let's talk about the other quantities. So P of no disease. So again, since we can consider this like the whole sample space, and so here is, we'll try to sort of draw it to scale, unlike before. So the actual disease part, that should be very small because it's only 1%. So here's disease and here's no disease, but this forms the whole sample space. So this would be the complement of that one, right? So that would be 1 minus 0.01, or this should be 0.001 because it's 0.1%. So this should be 0.999. And the final thing we need is probability of a positive test given that you have no disease. Okay? And so what I wanted you to notice here is that we don't actually know this quantity, right? So this should be part of the givens. Okay, so when we talk about accuracy, I mentioned above that there are two different kinds of accuracies we can speak of, right? So there's the true positive rate, which is how often we get a true positive given that you have the disease. But we can also speak of the true negative rate. So what is the probability that we say you don't have the disease if you actually don't have the disease? And similarly, probability that we say it's a positive result given that you don't have the disease, right? Remember, that's a false positive. And actually, this made me realize that I circled the wrong thing here. So when trying to talk about these quantities, I circled this, which is not right, so I'm going to erase that. Okay, so this corresponds to when you actually have the disease. Okay, and this portion corresponds to when you do not have the disease. Okay? And so the assumption that you need to make, given only the information in this problem, is that you're getting 99% accuracy in both cases. So it's 99% for saying positive test when you do have the disease, but it's also 99% for saying negative tests when you don't have the disease. Okay, so we're going to say this is 0.99 and this is 0.01 as well. Okay, so let's go back down here. And so this is when you're incorrect. So we'll say this is 0.01. Okay, and so now we have everything we need to compute the result. Okay, so for P of positive test, that's P of positive test given that you have the disease, probability that you have the disease, plus P of positive test given no disease, P of no disease. And this is equal to 0.99 times 0.001 plus 0.01 times 0.999. Okay, and this is equal to, you can try this on your calculator, it's 0.01098. Okay, and so now we're going to apply Bayes' rule. So Bayes' rule, P that you have the disease, given positive test. This is equal to P of positive test, given you have the disease, P that you have the disease, and P of positive test. And this is equal to, so just using the quantities above, 0.99 times 0.001 divided by 0.01098. Okay, and this is equal to approximately 0.0902, which is the same as 9.02%. Okay, so that's always a surprising result when you see it for the first time. So what this is saying is that given this level of accuracy, 99%, even with, I don't know why this extra line is here. This should just be D given plus. Even with that high of an accuracy rate, when you get a positive test, it still only gives you a 9% chance of having the disease. Okay, and so what does this do to? So intuitively, this is because the disease is rare. Okay, and so this is a little bit advanced, but I think if you've studied Bayesian machine learning with me before, this might be interesting. So ignore this if you've never studied this before. But if you have studied Bayesian machine learning with me before and you came back to this course to refresh your probability, this might be interesting. So really there are two quantities we're discussing here, which is two quantities. One is the test result, and two, our prior knowledge. Okay, so our prior knowledge is, do you have the disease knowing nothing else at all? So that's P of disease. And then the test result is P of plus given D. And so what Bayesian machine learning and Bayesian statistics does is it combines this knowledge together in order to tell us, what do we think now, given that you have the disease? So this is like an experimental observation. Okay, so what Bayes' rule really does is it helps us combine knowledge together. Specifically, what did we know before we did an experiment? What do we know after we've done an experiment? And how do we quantitatively combine those two sources of knowledge to update our uncertainty about something? Okay, so Bayesian statistics and machine learning is all about how to combine these two sources of information. Okay, so in this lecture, we're going to talk about another important concept called independence. So that's independence. Okay, so it should be pretty intuitive, but I will give some motivating examples to start with. So let's think of a situation first where we have two events that are not independent. Okay. So let's say we want to know, does a person have, so this is an example, does a person have long or short hair? Okay, so this is our, we'll call it our A variable. And our B variable is whether that person is male or female. So gender is either male or female. Okay, and this is B. Okay, so intuitively, we know that the probability that you have long hair, given that the person is female, is probably greater than P of long hair, given that you're a male. Okay, so in other words, it seems that these two variables are related somehow. Okay, so A and B are related, and and knowing one affects how much we know about the other. Okay, so let's think about whether it works the other way too. So if you know that a person has long or short hair, would that help you determine whether that person is male or female? And the answer is yes, right? So we could say also that P of female given long hair is higher than P of male given long hair. Okay, so now let's think about another example where we actually do have independence. Okay, so example, suppose we roll a die and flip a coin. Okay, so the results, the possible results, so the sample space is essentially all possible combinations. Okay, so basically it's every possible combination of heads and tails, and then 1, 2, 3, 4, 5, 6. Okay, so we've got, so for example, 1 heads, 1 tails, 2 heads, 2 tails, and so on and so forth. Okay, so we'll say 1 heads, 2 heads, all the way up to 6 heads, and then we've got 1 tails, 2 tails, all the way up to 6 tails. Okay. So now let's think about, for example, if we want to calculate the probability of getting a 1, given that the coin result, when we flip the coin, we got heads. Okay? And so using the rule of conditional probability, this would be the probability that we get 1 intersected with when we get heads, divided by the probability that we get heads. Okay, and so this probability, so this is the intersection of these two events. So when do we get 1? That's here. When do we get heads? That's here. Intersection is this. Okay, so that's, since there are 12 possibilities, that would be 1 over 12. And then P of heads, that's just 1/2. Okay? And so this is equal to 2 over 12, which is 1/6. Okay, so what is interesting about this is that it doesn't seem that knowing that we got heads has any effect on the probability of the die roll, probability that we get 1. Because as you recall, probability that we get 1, just with a die roll by itself, is also 1/6. Okay? And so let's formalize what we've discovered. So this is a definition. Okay, so it says that two events, A and B, are independent. Okay, so this is a very specific meaning in probability if the probability of A intersected with B is equal to the probability of A times the probability of B. Okay? And we didn't look at it in this form above, but let's see if we can manipulate this to look like what we've just seen. Okay, so notice that. So if A and B are independent, then P of A given B, this is P of A and B divided by P of B. But we know from above that P of A and B would just be P of A times P of B. So that's P of B. But the P of B's cancel out. Okay, so you get P of A. So what this is saying is that knowing B does not tell you anything extra about A. So knowing B doesn't change uncertainty about A. And similarly, P of B given A, and you can do this calculation yourself, is just P of B. Okay. Okay, so another important thing to know is that we can extend this definition to multiple events. So a collection of events, A1, A2, and so on and so forth, are independent if P of, or we can say mutually independent, if probability of AI1 intersected with, okay, so on and so forth, up to Aij, and this is equal to P of AI1 multiplied all the way up to PAIJ. Okay, and so why are there two indices here? Because these are subsets of events. So this is for any finite. So it's also finite. That's why we end at J. Subcollection. And this is AI1 all the way up to Aij of distinct events. Okay, so basically what this is saying is that there isn't just one condition, it's actually multiple conditions where you can take any subset of events and this will still be true. Okay, otherwise, if we just have P of AI intersected with Aj equal to P of AI times P of Aj, and this is for all I and J, and we call it pairwise independent. Okay? So what is the difference between the two? So let's do a quick example to see how this works. So example. So events A, B, and C are independent if all of the following conditions hold. Okay, so we have all subsets. So A intersect B, this must equal to P of A times P of B. P of A intersect C, that must be P of A times P of C. And P of B intersect C, this must be P of B times P of C. Okay, and we must have P of A intersect B intersect C. This must be P of A times P of B times P of C. Basically, it's saying all of these conditions must hold, not just, for example, these ones. Okay? And so we can do an example. So let's say we have our sample space is equal to 1, 2, 3, 4. And we'll say P of 1 is equal to P of 2, equal to P of 3, equal to P of 4, which is 1/4. Okay, and now let's say we make some events. So let's say A is equal to 1, 2, B is equal to 1, 3, and C is equal to 1, 4. Okay, so let's see which of these conditions is true. So P of A and B. Okay, so A intersect B, that's 1 by itself, so that's 1/4. And is this equal to P of A times P of B? So if we could check P of A, that's if we get either of these two, right? But getting each of them is 1/4. And these are disjoint events, right? So this is just P of 1 plus P of 2. So that's 1/2. P of B, similarly 1/2. And P of C is also 1/2. So this is equal to P of A, 1/2 times 1/2, which is P of A times P of B. Okay, so that part we've confirmed, that particular condition. And we can do the same thing because we have the same numbers for every different combination, right? So P of A intersect C is equal to P of A times P of C. And similarly for P of B intersect C, this is equal to P of B times P of C. Okay, but what about P of A intersect B intersect C? Okay, so again, the only element they have in common is 1. So this would be equal to P of 1, which is 1/4. Okay, but this is not equal to P of A times P of B times P of C, because that would be 1/4 to the power 3, or 1/2 to the power 3. Okay, so A, B, and C are not mutually independent. So they're mutually dependent. But they are pairwise independent. So pairwise independent, not mutually independent. Okay, so in this lecture, I want to expand on the concept of mutual independence with an example. Okay, so mutual independence for four events. Okay, and I think the sort of general version of the statement of the requirements for mutual independence are a little bit abstract, and so I think just doing examples makes it much clearer. Okay, So suppose we have 4 events, A, B, C, D. What are the conditions that we need for mutual independence? Okay, and so basically it's just every possible combination of 2, 3, or 4 of these variables. Okay, so every subset of events. Every subset of combinations of events. Okay, so here are the conditions. Okay, so we have the pairwise conditions, of course. So P of A and B should equal to P of A times P of B. P of A and C is P of A times P of C. P of A and D is P of A times P of D. Okay, and then we move up to B. So we have P of B, and we already did A, so now we only need to do C. And that's P of B times P of C. And we combine P or B with D. That's P of B times P of D. And then we have C, so there's no more left, so we go up to C. And for C, there's just D left. P of C times P of D. Okay? So that's just for pairwise. Now we can call this three-way. Okay, so what are all the possible triplets we can have? So we'll start with P of A and B and C. So that should be P of A times P of B times P of C. We can also switch out C with D. So we have A, B, and D. And same condition, P of D. And then we move up. So now we'll change this one. So we'll change that to P of A and C and D. P of A, P of C, P of D. And there's no more for the second one, so we'll change the third one. So we'll change this to B. So P of B and C and D. And by the way, if you think I've missed one, please try to come up with it yourself and let me know on the Q&A. P of B, P of C, P of D. Okay? And then, of course, we have the four-way one, of which there's only one possible combination because it's everything. So P of A and B and C and D. They should be equal to P of A times P of B times P of C times P of D. Okay, so those are the conditions for all 4 events, A, B, C, and D, to be mutually independent. Okay, so in this lecture, we're going to look at a very useful technique called the probability tree, or probability tree diagrams. Okay, so that's probability tree diagrams. Okay, and so what are these useful for? So this is a type of diagram that helps us list out all the possibilities of a sequence of events and compute their probabilities. Okay, so that's the key thing here, is we want to look at a sequence of events or outcomes. Okay, so it's a type of diagram that helps us list out all possibilities of a sequence of events and compute their probabilities. In other words, the probability of the whole sequence. And there are other useful applications as well that we'll see later. Okay, so what are some examples of sequences of events? So one example is flipping a coin multiple times. So flip a coin multiple times, or flipping a coin and then rolling a die. Flip a coin, then roll a die. Okay, and so I'll give you a more real-world example after this, but I want to show you what this tree diagram actually looks like. Okay, so let's say we were to flip a coin 3 times. So example, flip coin 3 times. Okay, so what would that diagram look like? So we'd have a root node, and the first coin flip comes out of that root node. And so we either get heads or tails. And we'll say for now, probability of each is 0.5. Okay? And so from here, so this was the first outcome. Our second outcome branches off from there. So again, we can get either heads or tails. And if we got tails first, we can still get heads or tails on the second roll. And again, that probability is 0.5 for each not roll, flip. Okay? And so again, for the third trial, same thing. Heads, tails, heads, tails, heads, tails, heads, tails, and all the probabilities are 0.5. Okay. And so there are a few useful things you can see from this. So one is that you can see the path through all the different outcomes. So for example, here's getting 3 heads in a row. Here's getting heads, tails, heads. Okay. Okay, so now let's look at another example, a more real world example. So example in finance. So here's the root node, and our first thing that we want to know is, are we in a bear market or a bull market? So we'll say bull market and bear market. Okay, and from here, so it's not going to be like above where we have the same thing every time. It's going to be different. So the second thing we're going to look at is whether the stock price will go up or down next week or next month. Okay, so up, down, up, down. And so this example is a little better than the previous one because we're actually going to have different probabilities for each of these branches. So let's say, for example, there's a 60% chance we're in a bull market right now and a 40% chance we're in a bear market. Okay. And now you get to see how these dependencies work as well. So unlike above, where the probability of a coin flip is always the same, no matter what you got in the past, as you can imagine from the physics of a coin flip, this is not like that, right? So if we were in a bear market, there's probably a higher chance that the price will go up tomorrow. And if we're in a bear market, there's probably a higher chance that the price will go down tomorrow. Okay, we'll say, so there's a 70% chance, or I said tomorrow, but we could mean whether we mean next week or next month or next year. All the same idea. Okay, so there's a 70% chance that it'll go up next, say, month, or a 30% chance that it will go down. Okay, but if we are in a bear market, we might say there's a 0.4% chance, 40% chance that it goes up, and a 60% chance that it goes down. Okay? So really what this probability is, it's P of down given bear market. And this is P of up given bull market. Okay, so these are all conditional probabilities. which of course, if these events were independent, then they would just be the normal probabilities by itself, as was the case for the previous example where we had the coin flip. Okay, but in general, these are conditional probabilities. Okay, so now what can we do with these diagrams? Okay, so going back to here, the first example, suppose we wanted to know the probability that we get 3 heads in a row. Okay, what this really means, so this is sort of a shorthand notation, but what it really means, if we think in terms of sets, is that first flip is heads and or intersect. Second flip is heads and third flip is heads. Okay, so that's what we mean by P of H, H, H. So it's a joint probability as opposed to a conditional probability. Okay, and the rule is you just multiply all those probabilities together. So 0.5 times 0.5 times 0.5. In fact, for all of these, it's going to be the same. So really, the number itself is not important. It's what is the event and how do you calculate that probability. So the numbers themselves, they're always going to be the same. So for example, this one, the second row, that would be P of heads, heads, tails. And that would be this probability multiplied by this one, multiplied by this one. Okay, so you get the idea of how you calculate those. So for the second example, again, it's the same idea. So beside this branch or this leaf node, we would write P of it goes up and it's a bull market. And you multiply those two together is 0.6 times 0.7. This would be P of it goes down, or the market, the price, you know. And this is 0.6 times 0.3. And this is P of it goes up and it's a bear market. And this is 0.4 times 0.4. And this is P of the price goes down and it's a bear market. And this is 0.4 times 0.6. Okay, and so you'll notice another thing we can do with this diagram is suppose we want to know, suppose we didn't know whether it was a bull market or a bear market. So we don't know if it's a bull market or bear market, but we want to calculate probability that the stock market price goes up. So what would that be? So basically, we're going to use that rule we learned about previously. So you can think of, say this is up, and so this is our sample space again, and this is the bull side, and this is the bear side, and we want to calculate this part. Okay? So it's the same rule as before, where we have P of up and bull plus P of up and bear. Basically, you're just summing up all of the values here that have up in it. So it's this one plus this one. Okay? And as an exercise, you can check that these are all the possibilities in the sample space, all the possible outcomes. And so if you add all of these together, they should sum to 1. Okay? So the rules for a probability tree rule, there's a sum rule and a product rule. So we multiply along a branch, and rule, we sum at the leaves. Okay, so you can think of it like a tree branch. So this is the branch, and these are the leaves, and this is a branch. Okay, so hopefully these rules make sense in the context of the previous examples we did. Okay, and so as a final exercise for this lecture, and this is going to be applicable later on in this course, we're going to compute. So what is the probability of getting 2 heads in a series of 3 coin tosses? And we'll say probability of heads is theta. Okay? And so we can use our technique that we just learned in order to compute this. Okay? So we'll draw a tree. So there's theta probability of getting heads and 1 minus theta of getting tails. Second row is independent. So again, it's theta, 1 minus theta, heads, tails. Heads, tails, theta, 1 minus theta. And then the same thing, heads, tails, heads, tails, heads, tails, heads, tails, theta, 1 minus theta, theta, 1 minus theta, theta, 1 minus theta, and theta, 1 minus theta. Okay, so we don't need to compute. So we have 8 probabilities here. We don't need to compute them all. We just need the ones where there are 2 heads. So it's this one. It's this one. It's this one. And I think that's it. Okay, so it might be a little hard to see now, but the probability of this, so P of heads, heads, tails, that's theta times theta, so theta squared times 1 minus theta. This is heads, tails, heads. This is theta times 1 minus theta times theta. So again, it's theta squared, 1 minus theta. And this one, P of tails, heads, heads. This is 1 minus theta times theta, which again is theta squared times 1 minus theta. So the answer, probability of 2 heads in 3 tosses, we just add those up. Okay, so it's the same thing added 3 times, which means it's 3 times that. So 3 theta squared, 1 minus theta is the answer. Okay, so in this lecture, we're going to summarize everything we discussed in this section. Okay, so this section was all about probability basics. So we began with defining probability, and I think the most intuitive definition is the frequentist view, where we think of probability as the normalized frequency of an event. Okay, so the first way to think of probability is as a relative frequency. In this case, the probability of an event occurring is the normalized frequency at which it occurs. Okay, and so you notice that this is a theoretical idea, right? Because we will never do an infinite number of experiments, so we'll never reach n equals infinity. Okay, but theoretically, this is the concept. So if we did this experiment an infinite number of times, the probability of an event A is the number of times it occurred during the infinite number of experiments. And so this also reminded me of something that students would often come to me with, which is actually a mistake. And so this came up when I was teaching statistics, where students would say, well, why do we have to do all this maximum likelihood stuff in order to show that the best estimate of some probability is the count divided by n? And because they didn't like doing all that work in order to come up with the answer, their sort of workaround was to think, well, isn't this just the definition of probability? Which is not correct. Okay, so the definition of probability is not just this proportion done on actual data. It's what would happen if we did this an infinite number of times, which we will never do. Okay, and so that brought up another important distinction, which was between probability and statistics. So probability, which is this course, we're working with probabilistic values, etc., but we will never work with data in this course. Okay, so that's a big difference between probability and statistics. So in statistics, we will be working with data, and we will also be applying probability. But probability is actually a prerequisite to statistics. So we're doing stuff that resembles statistics, but without actual data. Okay, so next we noted that the above interpretation of probability doesn't always make sense. Okay, so for example, if we're listening to the weather forecast and the weather forecast says there's a 70% chance of rain tomorrow, this does not mean that if we repeat it tomorrow an infinite number of times, that 70% of the time it would rain. Okay, so it pretty definitively disagrees with that previous definition of probability. Okay, so this suggests that we should expand our definition of probability, or the way we think about probability, to include these scenarios as well. Okay, and in order to do that, we realize that a better way to think of probability is that it's a measure of uncertainty. And you might think that's somewhat subjective, which is true, but we can also do computation on subjectively derived values. And you'll actually see this a lot in Bayesian statistics as well. Okay, so the next thing we did, so that was all just for intuition. There was no math in that lecture when we were trying to define probability. But in the next few lectures, we were much more explicit. And just keep in mind, relative to the rest of this course, this stuff doesn't really matter all too much, right? So that's why I said don't dwell too much on the definition of probability. Even this stuff, like I would say, go through it once, but it's not something you're going to have to consistently think about throughout this course. Okay, so it's just formalities that have to appear in every probability course. Okay, so we start with defining sample space, typically use the Greek letter omega, and it's the set of all outcomes of an experiment. An event is any subset of omega, and this includes omega itself, also includes the null set. Okay, so the next component is a probability measure P, which assigns for each event A a probability value P of A. Okay, so you can think of this as a function. It takes as input a set and returns a number. And this number is restricted to be in the range 0 and 1. Okay, so this is our probability measure P. Note that P of the null set is 0, P of the sample space is 1. Okay, then we talked about probability models. So a probability model basically consists of everything we just discussed. So it consists of a non-empty set called a sample space, omega, a collection of events that are subsets of omega, a probability measure P that assigns a probability to every event, with P of null set equals 0, P of omega equals 1, and where P is additive over disjoint events. Okay, so this is our first hint of how we can do arithmetic with probabilities. Okay, so what it says is if we have disjoint events, A1, A2, all the way up to A infinity, we can find the probability of the union of those events as the sum of the probability of the individual events. Okay. So then we looked at properties of probability models. So you notice we did some diagram stuff too, like the Venn diagrams and the tree diagrams, but we're not going to consider those in the summary, just because it's kind of annoying to include images in this document. Okay, so in any case, we have the complement of A, which means everything not part of A. In other words, it's the set difference between omega and A. The probability of that is just 1 minus the probability of A. Okay, and as a corollary of that, we have the probability of an event A plus the probability of everything not in A that must equal 1. Okay, we have some other rules. So this concerns when we have two events. So if A is a subset of B, then probability of A is less than or equal to probability of B. If A is a subset of B, we have the probability of B equal to the probability of A plus this whole thing. So B, probability of B intersected with the complement of A. I think these two are probably more important than this one. I generally don't see this one. Actually, in fact, we don't really work with these too much either. So in any case, we have probability of the union of A and B, that's less than or equal to probability of A plus the probability of B. And then we have, and there's a little mistake here, this should be intersect, but the probability of A union B is equal to the probability of A plus the probability of B minus the probability of A intersected with B. This will be fixed by the time you see this document. Okay, so next we have the law of total probability, which says that for a set of disjoint events that form a partition of the sample space, so basically we split up the sample space into A1, A2, A3, and so on, and then B is another event, the probability of B is equal to the probability of A1 intersected with B plus the probability of A2 intersected with B, and so on and so forth. Now this rule might seem a little random, but we're actually going to be applying this a lot later in the course, specifically when we talk about joint and marginal distributions. Okay, so next we looked at conditional probability, so more arithmetic with probabilities. So conditional probability allows us to quantify uncertainty when we have partial information. Okay, so just as a general concept, knowing more information might help us make a decision because it would inform us and change our uncertainty about things we don't know. Okay, so the rule is, if we know B and we want to ask what is the probability of A given that we know B, this is the probability of A intersected with B divided by the probability of B. Okay, we can also rearrange this by moving P of B to the top, to the other side, to get the intersection of A and B. This is equal to the probability of A given B times the probability of B. Okay, and we also saw that this allows us to express the law of total probability in conditional form. Okay, and we'll see this often again when we talk about joint and marginal probabilities and Bayes' rule and so forth. Okay, so speaking of which, the next thing we talked about was Bayes' rule. And so what that does is it takes one conditional probability and expresses it in terms of the opposite conditional probability. In other words, we switch the order of what we know and what we don't know. Okay, and this is applications in Bayesian machine learning, statistics, and so forth. Okay, so the rule is the probability of B given A is equal to the probability of A given B times P of B divided by P of A. And how we get this is, of course, we essentially just rearrange this formula. Okay, so the next thing we talked about was independence. So we say that two events A and B are independent if and only if the probability of the intersection of A and B is equal to the probability of A times the probability of B. Okay, and using conditional probability, we can say that an equivalent form of this statement is to say that probability of A given B is equal to the probability of A. And at the same time, we can do this the other way to get that the probability of B given A is just equal to the probability of B. Okay, and so all this stuff that we're looking at now, so, oops, I scrolled up too far. So conditional probability, law of total probability, Bayes' rule, and independence are going to appear later in this course as well when we talk about random variables. And so just to give you a little preview, what we're going to do later is essentially we're going to have this exact same form, but it would be much more general. So instead of just two events, we're going to be able to show this for two random variables. Okay, so we also talked about independence for more than two events. And so when there are more than two events, we have the concept of mutual independence or joint independence. And this will only be the case if all possible sub-collections of those events are independent. Okay? Otherwise, if you can only show this for pairs, then what you have is called pairwise independence. So in this short lecture, I want to tell you about my suggestion box. The idea behind this is analogous to the kind of suggestion box you would find at a restaurant. You can write down your thoughts and leave them for the owner to look at to give them feedback so that they can improve your dining experience. In order to share your thoughts with me in my suggestion box, please go to lazyprogrammer.me/suggestions. Here you will find a simple form where you can tell me anything you like. I have a few suggested fields, but none of them are required. However, they would be helpful for me to know. For example, tell me your background. I think someone coming from a background in marketing is going to have very different feedback compared to someone coming from a PhD in physics. Tell me what course you are taking so I have some idea of what you are talking about. Obviously, the more specific you are, the better I can help you. Tell me how difficult you thought the course was. Was it too easy? Was it too hard? Tell me if there was something I neglected to explain. For example, was there some word that I used that you have never heard of? Was there Python code that you haven't seen before? Tell me what you thought was missing from the course, even if it was just something small, like you missed explaining this line of code. Were you looking for an algorithm that wasn't included? This is helpful for me, but it's also helpful for you because many times students are looking for an algorithm or an explanation in the wrong course. So I can say, actually, I teach that algorithm or I explain that thing in such and such course, and this isn't the right course, so have a look over there. Are there any topics you want to request that were not included in this course? For example, maybe you signed up for a deep learning course and you were looking for CNNs, but the course didn't have CNNs in it. Let me know. Finally, let me know your suggestions for future courses. If there's a particular topic you want me to teach that I don't yet have a course about, such as gradient boosting or transformers or even quantum mechanics, let me know. Finally, there is a big text box for any comment you want to write. You can write anything in this box and make it as long as you want. In fact, the longer the better. If you think I talk too slow or I talk too fast, let me know. If you think my prerequisite instructions aren't fair, let me know. I want you to be as specific and as detailed as possible. A lot of the time people give me comments that I can't really act on, which is unfortunate. And this is often because they are too generic and not specific enough. Tell me exactly what lecture and exactly what timestamp you're referring to. If you want to refer to a question on the Q&A, include a link. Be very specific and give me concrete examples so that I know exactly how to act on the information you've given me. Thanks for listening, and I'll see you in the next lecture.